Hi everybody. In today's lecture, I'd like to talk about how to create electric fields within VPython and how to model the motion of charges that are under the influence of an electric field in VPython as well. So first, before we get into all that, let me remind you of a little bit of the basic physics that we're going to be using today. So charges, of course, are what are going to establish our electric fields here. We're going to show in VPython the charge, the source charge, and then in later code also the charge that's affected by the source charge. So the equation to describe the electric field due to a single point charge is E is equal to kq over r squared times r hat. Now here k is the Coulomb constant. I know k can mean a lot of different things, but here it's the Coulomb constant, which in SI units is 8.99 times 10 to the 9th Newton meters squared per Coulomb squared. And Q is the charge in coulombs, and R is going to be the distance from the source charge to the point in question where you wish to know the field. Now, of course, the electric field is a vector quantity. Remember that electric fields point radially outward from positive charges and radially inward towards negative charges. Now, the sign of the charge kind of gets sucked up into this Q right here, okay? But the R hat indicates the radial dependence there of the electric field. Now, if there's lots of charges and not just one, then remember that your electric field is going to obey superposition. So that means that the total electric field at a particular point in space is the vector sum of the fields from all the sources at that point. And so you would just sum up those equations. Now, we're going to use later, electric fields exert forces on charges. So the equation to describe that is F is equal to QE. Now, please don't get confused here. In the original, this is the source charge Q, and then over here, it's whatever Q is under the influence of the field created, okay? But the force on a charge in an electric field is F is equal to QV. Now, that can, of course, by Newton's second law, cause an acceleration. And so Newton's second law says that F equals ma, and so if you want to know what the acceleration is, you just set ma equal to QE and solve for a. Of course, m here is the mass, and a is the acceleration. All right, so let's just do a simple example first. I'm going to start off with just one charge, and then I'm going to show you how to visualize that charge, visualize the electric field from that charge with an arrow. So the problem I'm going to pick on here, I really could pick on a lot of different ones, but the one I decided to pick on is number 27 in chapter 13 of Matter and Interactions, which is our textbook for this course. So you're going to try and calculate an electric field at a point of interest or location, 0.5 minus 0.1 and 0.5 minus 0.5 meters. So those are the x, y, and z coordinates, 0.5 meters x, minus 0.1 meters y, and minus 0.5 meters z. So that's your location of interest, and it's due to a charge of plus 9 nanocoulombs that's located at minus 0.6, minus 0.7, and minus 0.2 meters in the x, y, and z respectively. So then the question kind of takes you through exactly how to calculate the electric field. It walks you through the process. And so we're going to walk through the process on how to do this in both analytical, handwritten way, and then also with VPython. And we're going to do a side-by-side comparison of those things. So part A says, what's the source location? Part B says, what's the observation location? C, what's the vector r that points from the source to the observation? What's the magnitude of that vector? What's the unit vector? And what's the magnitude of the electric field? And then finally, what is the electric field expressed as a vector? And so you can see that those steps are the ones that you exactly need to follow whenever you need to calculate an electric field. All right, so I've got on this next slide a link to my code, which I'll show you in just a second. And then I'll also answer the questions using both math, analytical written method, and then how you would do that same thing within the VPython code, and then I'll show you the code and we'll go through it together. So part A says, what's the source location? And I've copied and pasted from the question the locations of both the source and the point of interest and the charge here so we can do it all together. So what's the source of location? The answer in math would be the vector given here. Minus 0.6, minus 0.7, and minus 0.2 meters are the coordinates of the charge itself, which is the source of location. So that's how you write it out in handwriting, right? Or typewritten. Now, how would you tell VPython what the source location is? Well, you would use a vector, okay? So the way that I did it in my VPython code, of course your variable name might be different, but I created a variable called rSource, which I named a vector, okay? I told VPython it was a vector, and then I gave the coordinates. So this is how to do it in math, and this is how to do it in VPython, okay? Now part B says, what's the observation location? Okay, well, the answer in math, I just copied and pasted from the question. The point of interest where you want to know the electric field is 0.5 minus 0.1 and minus 0.5 meters for the x, y, and z coordinates. So copy and pasting that from the question, there's the answer, and that's how you'd write it out in an analytical way. Now, in VPython, what you would do is you would specify the position vector, okay? So I called that r underscore obs. I named it that variable. Of course, you could use a different variable. You could call it happy fun time if you want. It doesn't matter. VPython doesn't care. So r obs equals vector, and then I give the coordinates. So that's how you do that same step in VPython. Okay, next. What is the vector r that points from the source location to the observation location? Okay, so here's how to do that longhand, right? You have r, which is equal to r obs minus r source. So then you just subtract off those two vectors, and you find out that you get a vector r, which points from the source to the observation location of 1.1, 0.6, and minus 0.3 meters. And remember that when you're doing vector addition or subtraction, you do the components in turn. So for example, I got 1.1 by doing 0.5 minus 0.6, which gave me 1.1. And then I did that for each component. Now, how would you do it in VPython? Well, all you have to do is tell VPython, hey, I have a new variable. I'm going to call it r. And this new variable is the subtraction of my already named variables, r obs and r source. So r is equal to r underscore obs minus r underscore source. And now VPython knows what that vector is. Okay, what's the magnitude of that vector r? Well, in math, the magnitude of a vector is the square root of the sum of the squares of the components. And so that's what I've done here. And of course, that would be r is equal to the square root of 1.1 squared plus 0.6 squared plus minus 0.3 squared, right? And then when you find that square root, you get 1.29 meters approximately, okay? Now, how would you do that in VPython? Well, there's a one-step, one-line command to find the magnitude of the vector. Of course, you could tell it to do the exact same steps, you know, express and type all that out, but this is much shorter. To find the magnitude of a vector, you can just do mag of r, right? So mag is a command which finds the magnitude of the vector. So I did in my code rmag, which tells me, yeah, that's a new variable and it's just a scalar and it's just the magnitude of that vector. Rmag is equal to mag of r. There you go. A lot quicker, right? Okay. Part E says, what is the unit vector r hat associated with that vector that points from the source to the observation location? So what's r hat? Well, in math, what you would have to do is take your vector r and divide it by the magnitude of that vector r. So that would be 1.1, 0.6 minus 0.3 meters. That's my vector r. And then I would divide it by the magnitude of that vector, 1.29 meters. Now what that would do is you do it component-wise. You would take 1.1 and divide it by 1.29, and that gives you 0.85. 0.6 divided by 1.29 gives you 0.47, and so on and so forth, okay? And so this gives you the unit vector associated with r, all right? And it's 0.85, 0.47, and minus 0.23. That's our unit vector. Now, how would you do that in VPython? Well, I created a new variable. I called it r hat, right, to indicate my unit vector. And you can do it one of several ways. You could actually tell VPython to take the vector r and divide it by its magnitude. You could do that. Or you could use the command r hat is equal to hat of r. That's another way of finding the unit vector in VPython, is to use the command hat. Or you could tell it norm of r, and norm is also a way to find the unit vector. It's a command to find the unit vector. So that's what appears in my code, okay? Now, what's the magnitude of the electric field, okay? Well, the way to do that in math is to take K multiplied by Q and divide it by the magnitude of R squared. So K is 8.99 times 10 to the 9th. Q would be 9 nanocoulombs, so that's 9 times 10 to the minus 9 coulombs. And then you divide it by the distance from the observation to the source, and that's 1.29 meters squared. So doing all that, sticking it in SI units, you get 48.7 newtons per coulomb for the magnitude of your electric field. So that's how to do it. How would you tell VPython to do that exact same thing? Well, I created a variable. I called it Emag for the magnitude of the electric field. And I said K times Q divided by R mag squared. Now remember that the way to do squared in VPython is the 2 asterisks, not the caret symbol. That's always something I have to remind myself of every single time, okay? All right, now earlier in the program, and I'll show you this, I had already defined variable K and Q, and I told VPython that K was 8.99 times 10 to the 9th, and I told VPython that Q was 9 times 10 to the minus 9, and I'll show you that, okay? Now, you want to calculate the electric field at a specific location. We've calculated the magnitude, but we want to express it as a vector, okay? So what you do to find that electric field is you take the magnitude of the field, which we calculated in the previous step, and multiplied it times the unit vector there, which we also calculated earlier. When you do that, you multiply the magnitude, 48.7 newtons per coulomb, times each of the components of the unit vector in turn. And when you do that, you end up with the electric field vector of 41.5, 22.7, and minus 11.3 newtons per coulomb are the components in the x, y, and z respectively. Now in VPython, all you have to do is tell it, okay, the E field is that magnitude, Emag, times R hat, and you're done. And there it is. All right, so now that I've shown you all of that, let's go ahead and show you the code. So here's the source code, and this is online if you'd like to look at it. This is a public one. Now remember that the comments here are have the hashtag in front of it so that I can explain what I'm doing without VPython getting all confused. And here's some of the things that I already told you about. There's the commands. I just copied it and pasted it into the PowerPoint from my code, so there they are. And then also you can see here that I had defined the variables K and Q at the very beginning, right? Now what I did to visualize the magnetic field, and this is the only other, or the electric field, and this is the only other thing I need to tell you, is that I visualized it as an arrow. Okay, so the field is an arrow. I put it at the position of the observation point variable, which was R_obs. I made it orange, and I added a scale factor in because, of course, your arrows, your field might be quite large or quite small, and so you might want to blow it up or shrink it to have it fit in the field of view, and that's what scale factors are good for. So I just created a scale factor of 0.08 and multiplied it times the magnitude of my field so that when I run the program, which I'll do right now, it doesn't look too huge compared to my source charge. Okay? So there it is. Okay, that's my code, and it was pretty straightforward and simple, and I hope that you understood that, but let me know if you have any questions. Okay, so that's super simple. One charge, one observation location. But it's also maybe it's a little too simple, right? Maybe what you really want to do is create some kind of map of what the electric field looks like all over space, okay? That would probably be more useful for, most visualizations. Now, if you wanted to map that electric field for multiple points in space, it could be quite time consuming because you saw we just went through how to do all that by hand, and it was kind of tedious, right? But if you learn to code, you can create maps like that in a fraction of the time. So let me show you. I created another set of code, and this is for another problem in section 13.9 of your text under the section mini observation locations, and I duplicated their code and added some comments in there. So this is that. So let me pull that code over here. So this is shown here. Now let me run it for you so you can see what I'm doing first, and then we'll go back and take a look at the code. Running the code, you have a source charge here indicated in red, and then what we're doing is we're looking at the electric field that creates a map in a circle. Now the circle isn't centered on the charge so that you can see how the electric field actually depends very strongly on the distance from the source charge. So you can see here that when you're closer to the electric field, or when you're closer to the source charge, the electric field is much larger than it is when you're further away because of that 1 over r squared dependence. So this is a really nice visualization tool for that, okay? So that's what the code does. And now let's go back and look at the program. Okay, so the front matter is very similar. What you're going to do in your front matter is define your constants and define your charges. So I called K 8.99 times 10 to the 9th. The matter and interactions textbook calls that oofpez, but that's kind of long and I didn't want to type all that, so I just called it K. QE is the value of the source charge. And in this example, it's 1.6 times 10 to the minus 19 coulombs. It's like a proton, for example. Now, the scale factor is 3 times 10 to the minus 16. That is just to adjust the length of the arrows because I didn't want my arrows to be ginormous, okay, and I wanted them to all fit in the field of view. Now, I want to visualize my source charge. I do that by creating a sphere at the position in question. Now, this problem wanted us to place the source charge 5 nanometers to the left of the origin. So remember in VPython, X on the screen runs left to right, Y runs up and down vertically, and Z runs into and out of the screen by default. Of course, you can rotate your view as needed, but that's how it all starts. So this is 5 nanometers to the left of the origin. I made the radius of my charge 1 nanometer. Of course, protons are really much smaller than that, but okay, let's go with it, okay? And I made it red. Okay, then I said that my source charge was equal to QE, okay? And I do this later in case you want to switch out, go through your source charge, iterate it. Maybe you're going through a lot of sources, but anyway, there's that defined. Now, what I've done in this code is to create a circle that's offset from the center. And in order to go through and look at different observation locations on this circle, what I'm going to do is run through values of theta in certain size steps. But I also want to tell my loop when to cut off. So my maximum value is going to be when we finish going through the full circle, and that's 2 pi radians. So I say theta max is 2 pi, okay? Now my d theta, that's going to be my step size in my angle. And I wanted to do, say, 30 degrees, okay? You could change it depending on the problem or depending on the detail level that you want in your map. But I'm going to say that my d theta, which is my delta theta, how much I'm stepping in each iteration, is 30 degrees. So that's pi over 6. Remember that in VPython, the default value for angle is in radians. And if you want it to not be in radians, you have to do something about it. Okay, you have to tell it to go in degrees or whatever. But here I just stuck to radians. Now, I wanted to dictate what the size of my circle is. So I wanted to look at a radius of about 10 nanometers. So I said that my big R, which is the radius of my circle, is 1 times 10 to the minus 8. Okay? Now, when you start a loop, you have to give an initial value for the variable that you're going to change in the loop. I call that variable theta, and I set it equal to 0 to start. So while theta is less than theta max, right? Remember that when you first enter the loop, the value of theta is 0, okay? So 0 is less than 2 pi, yes, okay? So we're going to go into the loop. I give it a rate so that the visualization doesn't look crazy. And then I say, okay, my observation location, right, is going to be r times the vector of cosine theta, sine theta, and 0. So what I've done is the source charge is 5 nanometers to the left of the origin, but I wanted to see that dependence of the electric field on distance from the source charge, and so I'm going to look in a circle that's offset from my source location, all right? And I do that by choosing it to be at the origin. So what's going to happen is it's going to draw a circle whose center is the origin, and then it's going to look at the perimeter of the circle in 30-degree increments as it walks along. So my observation location is R, which is 10 nanometers, times cosine of 0, sine of 0, and 0 to start off with. And then, as it goes through the next iteration of the loop, it'll be cosine 30 degrees, sine 30 degrees, 0, right? And then next iteration, cosine of 60 degrees, sine 60 degrees, 0, and so on and so forth. All right, so my vector in my electric field, remember that the electric field is kq over r squared times r hat. Here r is the vector that points from the source to the observation location. So I have to define my vector r that's going to plug into my electric field equation, and r is r obs minus source dot pos. Remember that I defined my source with a sphere here, and my position attribute for my sphere is a vector of minus 5 nanometers 0, 0. So that's what happens here. It goes through and it takes the observation location, subtracts off the source to get that value of r. Then I have to also know what the unit vector associated with r is. So r hat is r over mag r. I could have also used hat r or norm r for this, but that's what I chose to do. Okay, now I'm going to find my electric field, and the electric field at that location is k times the source charge, q source, divided by the magnitude of my vector r squared, kq over r squared, right? And then times r hat, and that will give me a vector, right? Because all this stuff right here, that's a scalar. And then I multiply it times the r hat vector to get the direction of my vector. Then I'm going to visualize that electric field with an arrow. So the arrow is going to be positioned at the observation position. So the position attribute of my arrow is r obs. I'm going to make it orange, and then I'm going to multiply it by the scale factor so it's not enormous, okay? And I'm also going to make the width of the shaft the same size as my visualization of the sphere so it doesn't get super fat, okay? After I visualize it, after I draw my arrow, I'm then going to increment my value of my angle by 30 degrees or pi over 6, and then it'll go back through. And it'll do that as long as theta is less than theta max, and so it'll walk in a full circle around, okay? Running the code again, you can see that's what happens here, okay? All right, so I hope that is straightforward and easy to understand. Okay, now another reason why coding is a really great thing to do, and physics majors should definitely learn to do it, is that the acceleration of, say, a test charge, usually when we say test charge, we mean a tiny little charge that doesn't distort the electric field of interest in the region, okay? So the acceleration of a test charge under the influence of this system wouldn't be constant, right? The reason is that let's say that you have these source charges and they're fixed. You put your test charge in there. What will happen is that test charge will feel a force from the source charges via the Coulomb force, and it'll start to move. But the Coulomb force itself is dependent on the distance between the source and the test, right? And so as that distance changes, the force itself will change. So you've got an acceleration which isn't constant, okay? And depending on the location of all the source charges, it could be quite complicated to figure out, and it gets really tedious to map all that out. So solving these kinds of things analytically would be quite complicated, but in terms of coding, the coding is pretty straightforward, okay? So let me show you what I mean by that with another example from Matter and Interactions. This is number 47 from chapter 13 of Matter and Interactions, and this is our setup. We have a -4 microcoulomb charge located 3 centimeters up from the origin. We've got a +3 microcoulomb charge located up here in the upper right, and we've got a -2 microcoulomb charge located, say, what is that, 4 centimeters to the right of the origin. So at a particular moment, you've got those charged particles, they're, say, fixed. And then let's say that we have a particle with a charge of -3 nanocoulombs placed at A. Okay, now notice that the source charges are microcoulombs, okay, and the test charge is nanocoulombs, so in comparison it's much smaller. So we have that test charge of -3 nanocoulombs placed at A, so what would be the force on that particle? Okay, so that's what the question asks, but I'm going to do one better and actually even map the motion of the charge for you so that you can see it's not that bad, okay? So what we're going to do here is remember our iterative technique. And this was covered in some earlier lectures on VPython, the iterative force technique for mapping the motion of something using VPython. Okay, so remember, iterate means to repeat. And so this all goes within a loop. Okay, so here's what we're going to do within this loop. First of all, we're going to have our particle move around. Now, if it moves, the electric field is going to be different as it moves. It's not going to be the same field everywhere. So within the loop, we're going to have to calculate the net electric field at the location of that moving particle. Okay? So you're going to have to calculate the electric field at the point in question, due to each charge, and do the vector sum of the electric fields from all three of those source charges that I showed you on the previous slide. That's step number one. Then you're going to have to use the equation F equals QE to calculate the force on our little test charge at that point where you calculated the electric field. Yet again, this force isn't constant. It will change with position. Once you've calculated the force at that point, you're going to have to update the motion of the particle. You do that by updating its momentum using the momentum update equation. Remember that this comes from Newton's second law. If you take a short enough time step, you assume that your force is constant over the time step. So the way that you do that is say the momentum now, or P final, is equal to the old momentum, P initial, plus the net force calculated in the previous step, F net, times your time step delta T. Once you've done that, you're going to update the position of the particle using the position update equation. So you're going to move your particle, okay? So that is going to be the new position, R final, is equal to the old position, R initial, plus the average velocity during that time step, V average times delta T. Remember that we calculate our V average by taking the momentum from the previous step and dividing it by the mass of the particle, okay? So let's look at the code. Actually, I've already got it pulled up over here. I think this is it. Let's run it and make sure. Yeah, there it is. Okay. So this is what the code does. I started off with those charges as shown in the problem, and then I make the particle move with time. Okay, so let's take a look at it real close. Remember that in the beginning, in the front matter, we're going to start that off very similar to the way that we did our previous problems, in that I'm going to define my constants. I'm going to define the values of each one of my source charges. I called them Q1, Q2, Q3, and then for the moving charge, I called it moving Q. And then I defined it with the values set in the problem as shown. I gave the mass of the moving charge. Okay, so I gave it a big old mass. It doesn't have to be this. And of course, if you want to use this code, you feel free to, and then you can change it up for your particular problem. It's okay with me. Okay, now next, you define the positions of your source charges. So I called those for charges 1, 2, and 3, not very originally, R1, R2, and R3. Okay. Then I said, okay, my moving R location, I have to give it an initial position. And so I did that. I put it right here at 0.01, 0.01, and 0. Next, I gave it an initial momentum. I decided to let it start from rest. Okay, now I want to visualize all these things. I visualize my charges as spheres and I make them different colors. So you've seen this in old code too. I make the position attribute for each one of my source charges, the values of the vectors R1 and R2 and R3 that I defined earlier, and I made them blue and red. The blue is for negative charges and the red is for positive charges. Then I make my moving charge a different color, and I turn on the map, or turn on make trail so we can see its path as it goes. I define a time step. You could make this whatever you want. I decided to go with 10,000 steps per second. Okay. I initialize my clock. I'm going to start my clock at t is equal to 0. And then I decided just for fun that I would plot the magnitude of the force on that charge versus time. Okay, so here in the loop you can see it's not a super long loop. In this code up here, it's not very complex, okay? But what I've done is first I've calculated the vector r for each one of the source to moving charge locations. So within the loop, remember, you're going to have to calculate your electric field each time as the particle moves. So step number 1 of that is calculating the vector r in the bottom of the kq over r squared, right? So I've got that vector defined, moving r minus r1, minus r2, and minus r3 respectively for the 3 charges. I then calculate the unit vectors for those 3 charges, and then I find my electric field for each one of those 3 charges at the point in question in a way very similar to I did from the previous code. Now that I've got my 3 electric field vectors from my source charges set up, I then calculate the force on my moving charge by doing F equals QE. Specifically, that's F is equal to the moving Q times the sum of my 3 electric field vectors E1, E2, and E3. There you go. Then I update my momentum. P is equal to P plus F times delta T, right? Then I update my position. The moving charge position is now going to be its old position plus P over M. That's the momentum divided by the mass times the time step delta T. And then I update the value of where my source charge is displayed by saying that moving charge.pos is equal to my vector moving R. Okay, so that moves the actual source charge of visualization to the new location. I increment my time step, T is equal to T plus delta T. I plot on my force curve what my force is, what my new value of the force is, and that's it, and that's done. If you run the code, there it is. Okay, it shows the position, the trail is turned on so you can see where it was, and the particle moves. Okay, so that's that. So you can see that something that would be very difficult, we've moved from doing something that's super not too bad to solve analytically, solving for the electric field at a single point, right? Then we moved for solving the electric field in multiple locations due to a source charge, which was way quicker to do with the VPython code. Then from that, we've now got multiple charges, right, creating an electric field, and now we allow a test charge to move within that field, and you can see truly now the power of coding. All right, I hope that helps. Let me know if you have any questions, and as always, I'll see you in class.